No, I didn't. Okay, everybody, here's a very interesting integral and method that is specific to solving this integral. We have, I'm going to start this again. Okay, everybody, here's an interesting integral, and I have to admit that I tried a long time trying to find a suitable method to solve it, because the method that I found for solving this is very specialized. It's not a general method that can be applied to a broad range of problems, and it can only be applied under very special circumstances, as you will see. So this is the integrand, the square root of sine of x over the square root of sine of x plus the square root of cosine of x. And we use some trigonometric identities in order to solve this, but in a way that is not part of the general trigonometric methods that we use to solve a broad range of problems. This is only for a very specific problem. So what we do is we make a substitution in this. I tried all different kinds of methods. I just was not able to find a way through this except for this one particular method. And when you see this method, you'll see it ends up becoming a very trivial problem. So here we use a u substitution for the argument of the sine of x, where we say u equals pi on 2 minus x. And we end up with limits, changing the limits. So when x is pi on 2, x is pi on 2, u equals 0, and when x equals 0, u equals pi on 2. So our limits of integration actually invert. So we have pi on 2 to 0, and we have sine of pi on 2 minus u over square root of sine of pi on 2 minus u plus the square root of cosine pi on 2 minus u. Now, we know fully well from the trigonometric identities that this what we can do with this argument. But before that, we have to find what our differential is. So du is equal to minus dx. So minus dx is, or dx is minus du. Okay, so here in our arguments, we know that sine of pi on 2 minus phi is equal to cosine of phi. And that's just one of the very early trigonometric identities that we learned using right triangles. So that converts this problem from this argument here, or integrand, to cosine of u over square root of cosine of u plus square root of sine of u minus du. Okay, now we know that if we flip-flop the limits, we have to put a negative sign. So we put a negative sign there, and we go 0 to pi on 2 square root of cosine of u over square root of cosine of u plus square root of sine of u d minus du. But that's positive du. So the minus signs cancel out, and we have an equivalent form. Cosine of u over square root of cosine of u plus square root of sine of u du. Now, this initial integral is equivalent to this. Now we can substitute the argument u for x. So we have two ways of representing the same integral. So what we do here then is this. We say that I plus I, which is equal obviously to 2I, is equal to this first form, 0 to pi on 2 of square root of sine x dx over square root of sine of x plus square root of cosine of, let's make that neater. We make that a little bit nicer to look at. Cosine of x. But that's also added to this 0 to pi on 2 of square root of cosine of x dx over cosine of x plus sine of x. Now notice that what we have here is that the denominators don't change. And so we have similar denominators. We can add the integrands, and what we're going to do here is we're going to get a new sheet, and we'll complete this problem. And what we have is 2I equals 0 to pi on 2 square root of sine of x plus the square root of cosine of x dx over square root of sine of x plus cosine of x dx. Now, by combining those two integrands, we ended up with a ratio that is simply 1. So we have 2I integral of pi on 2, 0 to pi on 2 dx, and that is equal to, let's see, I'll write it better, is equal, so 2I equals x, pi on 2 to 0, and that's equal to pi on 2i. And so the solution to that integral is pi on 4. And that's what we've been working towards. And that's a trivial solution. It is phenomenal. Now, there is a generalization that can be applied, but it's only to this specific type of problem. And we'll go through that generalization in the next video. But again, it only applies to a certain class of or group of integrands, and it's not a major method that's going to help us out. I mean, it helps us in this particular case, but it doesn't. It's not one that's going to be really worth memorizing as the other methods are worth remembering. But it is good to keep in your hip pocket that this method does exist, and that you can indeed use it to solve certain types of integrals. But again, a limited family of integrals. So with that, we're done, and I wish you well, and we'll talk about the generalization in the next video. So this is Mathman wishing you all the best.